So welcome back again to the course on VLSI physical design, design compiler basics. So in the last class we have seen, that means how to set the libraries in the design compiler environment. So now we will see the other thing, that means how you can, that means read your library in the Synopsys environment, design compiler environment, as well as the other things which are related to design compiler. Okay. So the next thing is that working with the libraries, that means how you can load your libraries into the design compiler environment. So your actually that design that will be saved as .db format, or the symbol library which is been created for your design, that has been saved as .sdb format. So Synopsys design compiler automatically loads all these things. If you want to do it manually, so at that time you can write this command, that read underscore file mylib.db as well as read file mylib.sdb. So these two commands will read your library as well as the corresponding symbol library into the design compiler environment. So now if you want to see, that means what are the libraries has been created for your design, so that also you can visualize using this command, that means that is list underscore libs. Okay. So if you see that list underscore libs, that shows you that okay, this logical library is the library file path name is this one, and my symbol lib underscore my underscore symbol underscore lib, that is my lib.sdb on this that particular path. So that means where it has been saved, that it will indicate. Okay. So next is that reporting the library contents, that means what are there, that means what has been created inside your library. So the components are like this library units, then operating conditions, then value models, and the cells. That means what are the, so operating condition means, that means what is the that process you are using, what are the voltage you are using, what are the temperature condition you are using, as well as the well load model, that means what are the capacitance and resistance model you are using for your design. So all these things will be listed whenever you are actually, all these things will come whenever you have mentioned, that means as a constant file you have already given to the system. So now whenever it is done, so at that time it will show you that okay, these are the things which you have set for your design to be compiled in design compiler. So then next is the specifying the library objects, how you can specify, that means what are there in the library. So that thing can be done, that okay, if you write this command like set don't underscore use mylib / and4. So actually what does it means, that suppose in your design some of the cells you don't want to use, so at that time you can write this command, that set don't underscore use mylib / and4. If it is and2, so you can mention as and2. Then in some case it may happen that okay, one of the paths you don't want to like use, or you don't want to optimize, or you don't want to, that means at all, that means not at all the design compiler will touch. So at that time you can do one thing, that means write this command, that set underscore disable underscore timing, then get underscore pins mylib / and4 / z. So that means what it will do, so it will set that means this disable underscore timing attribute, that will set that that means this and4 cell z pin. Okay. So it will disable the timing information for that particular pin, as I have already mentioned through this command. Okay. So now suppose I want to like exclude a cell from my library. So how I can do that? So for excluding a cell from the target library, that means suppose in target library there are several type of AND gate, there are several type of OR gate, there are several type of basic gates, right? So how I can, that means whenever I am compiling, so at that time each of the cells, each of the, that means standard cell which has been mentioned in the library, that will be used So suppose I don't want to use one of the particular cells, so how I can exclude that cells from the target library. So at that time you just write this command set underscore don't underscore use mylib slash inv underscore hd. So inv hd is the cell which I don't want to use, so I have set that with this command. Okay. So then one thing you can do, that is, suppose this I have already said that okay, don't use this library. So I now for the next design I want to use this. So at that time how I can remove that, that means don't use command in the design compiler environment. That can be done through this command remove underscore attribute mylib underscore inv hd don't use. So it will do what? It will remove what attribute you have, that means what constant you have put, that means set underscore don't underscore use this particular cells. So now it will be again you can reuse this in the next design context. Okay. So then how you can verify the consistency which is persist in the library. So that you can check, you can just do by this command check underscore library in the design compiler environment. So all these things, whatever command I am telling you, that all the commands you can run only in the dc underscore cell environment. So then as I said that whenever I read one Verilog file, suppose my design file I have read into the Synopsys environment, so at that time it basically saves into a memory. Okay. So how I can remove the libraries from that particular memory? So whenever you just type like this list underscore libs. So what are the libraries you have mentioned or you are using for the current design, so that it will show you. Okay. So now if you want to just remove it, so at that time you just type this command remove underscore design. So remove underscore design will remove each and everything, that means whatever library you have mentioned, what design you have read, so everything will be removed from the Synopsys design compiler memory. Okay. So now again, before to start with another next design, so you have to do this remove underscore design, otherwise all these things all this information will be saved into the Synopsys memory. So how now next is that how I can save a library. So this write underscore lib command, that basically saves your library into the disk. Okay. So that maybe you can save into like .db format or .v format or .vhdl format, in any format you can save it. So then suppose as I said that in some of the case we are using some of the system design, we are using this intellectual properties like third party IPs. So they will be just seem like a black box to me. So we don't know what are the architectures or whatever blocks it is using inside of that particular block. So we will know that, we will not basically able to know that. So how you can handle those type of boxes whenever you are reading those boxes or you are using those boxes in your design. So at that time you can do that means one thing, that means there are three type of black box it is available. That means the functionality is unknown black boxes. That means at that time you don't know the functionality, what is basically that black box means. So at that time this indicates that these are cells where the logic functionality is not known to me, and this example include the following type of cells like macro cells, empty hierarchy cells, or black box module, or unlinked or unresolved cells. That means whenever there are like macro cells or this type of cells are there, so I don't know the functionality of these particular cells, but it is using, it has been used in my design. So how can I handle those type of black box? Then logical black box. So these are cells that do not link to a cell in the logic library. This type of black box is categorized under functionality unknown black box cells. Examples include the following type of cells like empty hierarchy cells, black box module, unlinked or unresolved cells. Then again there are another type of black box which are physical black box. These are the cells which do not have the physical representation. So, the examples are like empty hierarchy cells or unlinked or unresolved cells. So, that means in each of these black box when it will be created, like if any of the cells which is not at all used in the particular design environment, so at that time it will be known as black box to Q. Okay. So, then how I can define the timing of that particular black box. Okay. So, the first thing is that means quick timing model format for how I can set for black box model. So, all these things are basically the part of DC Explorer. That means how I can explore the design, that means design exploration we can do easily. Okay. So, as we have already discussed this in the earlier slides. So, the first thing is that how you can do. You can do, that means to run this you have to run, that means go to the topographical mode, not just the normal mode. So, you see that in DC cell topographical mode you can write this command create underscore QTM underscore model BB. So, BB is the model name now. Then specify the technology information such as the name of the logic library, the maximum transition time, maximum capacitance and the well load information. So, how you can set those? Set QTM technology minus library, the library name, then the set QTM technology minus max transition with the transition values, then set QTM technology minus max capacitance with the capacitance values. After setting all these things, that means now I have set the library for that quick timing model for that black box. So, BB indicates that black box. That means now we are defining the corresponding library or the corresponding capacitance well load models for the particular black box. So, after that what you can do, you can specify the global parameters such as setup time and hold time values. So, how I can set using this command set QTM global parameter minus param setup minus value with the setup time value, the same thing with the hold time value, and then the clock to output with the corresponding values. Okay. So, that means now if there is any clock in the black box, now I can set what will be the clock to output values, what will be the setup time values, what will be the hold time values, that I am setting now. So, after that what you can do, specify the ports. Okay. So, that means what are the corresponding input output ports are available on that particular black box model. So, that I have to define now. So, how I can define? With this create underscore QTM underscore port minus type input A, create underscore QTM underscore port minus type input B, so output OP. So, that means now I can say that okay, A and B is my input and OP is my output. So, I have set all these things for the, I am setting all these things to the particular black box. So, after doing this, that means after specifying the library information, well load information, then setup time, hold time values, clock values, and then input output ports, then what you can do, you can specify the delay arcs using this create underscore QTM underscore delay. That means now I will save or I will create the delay time, that means timing information for that particular black box model. So, how I can do that? Create underscore QTM underscore delay underscore arc with the name of this A to OP from A to the rise edge of OP with the values of 0.10. Okay. So, that means here you see that means now for the delay information, now what I am trying to do, I am creating the corresponding timing information, I am doing the timing modeling of that particular blocks. how I am doing, I am mentioning that okay, from A to OP, so rise time values will be 0.10, from A to OP fall time will be 0.11, then B to OP the rise time will be 0.15, B to OP the fall time will be 0.16. So that means each of these four comments sets what will be the transition values for input A to the output or input B to the output. Okay, and if for each of the, that means input to output, what will be the values of rise time and fall time. So initially we have set the setup time and hold time. Here what we are doing, here we are setting the rise time and fall time values. So after that, generate a report that shows the defined parameters, the ports and the timing arcs in the quick timing model. So how I can do that? That report underscore QTM underscore model. So once you have that means type this comment, so at that time it will show you whatever model I have set till now. So all these things will be shown in the DC topographical mode. So after that, you save this quick timing model using the save underscore QTM underscore model comment, and then you write out the .db file for the quick timing model using the write underscore QTM underscore model comment. Okay. So and here you have to you see that in the comment you have to mention the corresponding name. Okay, name of the directory where it will be saved. So after that, you can add this DB file, or you can add this that means black box library file into your corresponding that means now you can use it by comment this lappend link underscore library qtm/bb.tb, which has been already created. That means that library information I have created. Okay, so I have created that library information, I have saved it in particular QTM directory. Now I am using that library for my design in the rest of the part. So now the thing is that how I can this is that means this library now you can use it for that particular block. You can use it for in the design compiler environment. So that means this timing information, library information, so all these things I have said. So now how you can define the physical dimension. Okay, so physical dimension, unless and until you are providing the physical dimension itself, so at that time what will happen? So next time whenever that box now that you have to use in the physical design part also. So unless and until you are defining the dimension, whenever you will use that particular box in the IC compiler, so at that time it will create you the, or it will give you the problem. So how you have to model the physical dimension of that particular block too. So how you can do that? So estimating the size of black box. So to set the width and height, use the -sm underscore size option. So here you can write this command estimate underscore fp underscore black boxes minus sm underscore size with the size value. Whether that will be rectilinear shape or that will be rectangular shape, that you can mention with this command estimate underscore fp underscore black underscore boxes minus polygon with the polygon area, like that may be rectilinear or that may be rectangular. So after that, that means suppose okay, there is one example for that. That means the following example: estimate a black box named ALU1 and specify it as soft macro with a size of 100 into 100 with a utilization of 0.7. So how you can do that? You can write this command estimate underscore fp underscore black underscore boxes with the same size of 100, as the size is 100 cross 100. So 100 100, and this utilization factor is 0.7, and the that means the cell name is ALU1. So I have said that name as ALU1. Okay. So after that, what you can do, that means this next command, the following that means command estimate a black box named ALU1 and specify it as a rectilinear soft macro. So here you see that means that here this minus polygon, it basically creates the shape, and minus sm underscore size, this basically creates the size, that means what will be the height and what will be the width for that particular black box. So the shape is like, then we have to set the corresponding values for that shape, and the as the name of the black box is ALU1, so I have set that as ALU1. Okay. And now as I said that, okay, this is soft macro. Okay. So now if I want to design a hard macro like RAM blocks, so how I can do that? So the same things can be done, estimate underscore fp underscore black underscore boxes minus hard macros with the RAM of 16 cross 128 with the name is U1. Okay. So the RAM size is 16 into 128 and the name is U1. So what is my primary target here? That means now I am creating the macro blocks which will be used in the, that means for further design. That means whenever if I want to use these IPs for high level of design, so at that time I can mention the corresponding all this timing information, all this physical information about that particular cell, and after that I can reuse those the blocks in further of my design. Okay. So then the next is that how you can determine the gate equivalent area. Gate equivalent area means, what is the meaning of this and why I need to determine all, that means this gate equivalent area. Whenever I am synthesizing it, so at that time it shows me that okay, this much of that means cells I am using. So each cells corresponds to maybe corresponds to some of the gates. So like if I am using a gates, so at that time suppose I have used 10 AND gates, 100 OR gates or 5 XOR gates, something like this I have used in my design. So each of the gates information, that means the area information is already there in the library. So now whenever I will try to estimate what is the area consumption for my whole design, so at that time what are the number of cells I am using, and for each of the cells what is the corresponding area, that based on that it will create and it will show you okay, this much of area you are consuming for your particular design. So how you can do that? Using this command set underscore fp underscore base underscore gate minus cell with this unit is the name, and to specify the cell area in a square micron as the base unit, area to be used for the calculation, this minus area option you can use, that is set underscore fp underscore base underscore gate minus area, that is 10. So that means now I am setting the area values, what will be the area values for that particular black box that I am using. Unless and until basically I am giving all this information, whenever I will reuse this in my next design, so at that time I will not get the timing information, or I will not get the area information, or I will not get the power information about that gate. So the next thing is that identifying black box cells. So how I can identify a black box cells. So design compiler sets the following attributes on black box cells, that is this a black box with this comment is underscore black underscore box. So when you specify the is underscore black underscore blocks attributes with the get underscore cell command, design compiler identifies functionally unknown black box. So how you can do that? And you can write this command get underscore cells minus hierarchy minus filter with this command is black box equals to true. So if this is black box is true, then it will show you that okay, these are the black box which are unresolved or unconnected into your particular design. So there are another thing is that is logical black box. This basically attributes with the get cell command to identify the logical black box. Okay. That means here is black box, it can identify any black box, but if there is only logical black box, so at that time if you have to use is underscore logical underscore black underscore box is true or not. So if there is physical black box, that means the black box that may be created in the physical or in the logical domain or in general, that means with the timing information. So if in this physical information is missing or physically if it is unconnected, so at that time by this is underscore physical underscore black box, if that is true, it will identify those physically unconnected black boxes into your system. So working with the design in memory, as I said that okay, whenever we read something, that means in whether that is in Verilog format or in DB format, all these things are saved into the synopsis memory. So now reading the corresponding HDL, how you can do that? That you can use this read underscore file command, that means for reading the corresponding Verilog or VHDL file, and then this corresponding Verilog file or this VHDL file that will be converted into the generic, that means library, which is owned by Synopsys or provided by Synopsys. So then you have to run this analyze and elaborate command. The analyze command checks the design and reports the error, and the elaborate command translates the design into a technology independent design, that is GTech, from the intermediate files produced during the analysis. So running the read Verilog or read VHDL command, this commands check the code for correct syntax and build a generic technology library netlist file in the design compiler environment. You can also use this read underscore Verilog or read VHDL commands to do both functional, to do both functions automatically. Okay. So that means I can do actually these are the commands which I can use for reading the HDL files into the Synopsys environment. Okay. So for today up to this one, so we will talk the next that means next aspects of design compiler in the next lecture. Thank you.